Hello, everybody. Welcome back to Measure Theoretic Probability. In the last video, we were talking about independence of sets, sets representing for us events, so independence of events. And we all know from Probability 101 that the events A and B are independent if the probability of the event A intersect B factors into the probability of A times the probability of B. Now, in the previous video, we were talking about a larger collection of sets, a set of sets, or a class. So a class of sets is the same thing as a collection of sets, is the same thing as a set of sets. And if you have n sets in this class, collection, or set, then they are mutually independent if the probability of the n-way intersection factors into the n individual probabilities. And also, if you pick out any n minus 1 of those n sets, and there's n choose n minus 1 ways to do that, and you look at the probability of an n minus 1 way intersection if it factors into the n minus 1 individual probabilities. And if you look at any n minus 2 and n minus 3, and so on, and go all the way down to pairwise intersections, the probability of any AI intersect AJ should factor into the probability of AI times the probability of AJ, assuming I is not equal to J. Also, at the end of the last video, we kicked it up a little bit to cover an infinite collection of sets, either countable or uncountable. So if you have an uncountable or countably infinite collection of sets, we say they're independent if for any subcollection, any finite subcollection, so you choose any n, then go in there and choose any sets A1, A2 up through AN, if those are independent. And those are independent if the n-way intersection factors, and if you go in and look at any n minus 1 of those n sets and the n minus 1 way intersection factors, and any n minus 2, etc. So basically, we can talk about a collection of sets being mutually independent, even if there's an infinite number of them. It's just by definition, we look at every finite collection we want to look at. So in this video, we're going to move from sets in one collection being independent of each other to two or more different collections of sets being independent of each other. And the question I want to answer is, once we've defined what it means for two collections of sets to be independent of each other or more, what would happen if we took each collection and expanded them to be the sigma field generated by the collection? So we'd be throwing more sets into each collection, and are the resulting sigma fields generated by independent collections, are the sigma fields still independent? That's what we want to figure out in today's video, so let's get going. First of all, we need to define what it means for collections of sets to be independent. So I'm going to use these capital curly A1, A2 up through AN. So each of these are collections of sets. And we say that the classes are independent if not curly A1, not curly A2 out through AN. So individual sets are independent for any choices of AI in curly AI. Now, this is a loaded statement because these are independent if the n-way intersection factors, or if you choose any, say, n minus 5 of them, just as an example, that intersection has to factor, any two of them has to factor. So I think a much easier way to think about this, to maybe define independence, is to say that these classes are independent if the probability of A1 intersect A2 intersect out through AN factors into the individual probabilities, where each AI comes from curly AI, or each AI is equal to omega. So these curly A's, these are not fields or sigma fields necessarily. They don't have to contain omega. But if you throw omega in as a possibility for the AIs in this definition, then that takes care of the lower level intersections for you. For example, the three-way intersection, if you're looking at the probability of A1 intersect A2 intersect A3, and you allow A2 to be omega, then really you're looking at the probability of A1 intersect A3. So allowing omegas in there allows you to look at all those subcollections in intersections. As I already mentioned, today's goal is to say that if we have two or more independent collections of sets, now we just defined what that means, and we want to take the sigma fields generated by each, which expands each, are those sigma fields still independent? Unfortunately, the answer is no, as I'm going to show you in an example. But we're going to turn that answer into a yes by adding just a very simple restriction. So first, the failure of this statement. Consider flipping a fair coin twice. That means you have four possible outcomes: heads, 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 tails, tails, heads, and tails, tails. They're all equally likely, so the probability of any one of these outcomes occurring is 1/4. I'm going to define two classes of sets for you. These are sets of sets. Curly A1 is going to consist of two sets, each consisting of two elements each. The first set is heads, 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 tails, and the second set is heads, heads, tails, tails. Curly A2 is going to be a collection consisting of one set only, and that one set is going to contain two things, heads, tails, and tails, tails. Now, it's easy to show that curly A1 and curly A2 are independent. We have to look at various we have to pick a set from over here and a set from over here and intersect them and look at the probability. And there's really only two things we need to check. I'm just going to check one of them for you. So if I take the set heads, 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 tails from over here and the set heads, tails, tails, tails from over here and intersect them, I get the singleton set heads, tails. And the probability measure of that singleton set heads, tails is 1/4. Whereas the probability measure of both of these sets that have two elements in them is 1/2 each. And in fact, we do have 1/2 times 1/2 equals 1/4. So this set is independent of this set. And once you show that this set is independent of this set, then you've got that this class is independent of this class. So that's how you show that these two classes, curly A1 and curly A2, are independent. And my claim is that the sigma field generated by curly A1 is actually not independent of the sigma field generated by curly A2. I'm going to just pull out an example where this factoring probability thing is going to fail. So to make this a little easier to talk about, I'm going to name this set A, this set B, and this set C. And note that I can write C in terms of unions and complements and intersections of A and B. This isn't supposed to be obvious right off the bat. This took me a little while and literally the back of an envelope to work this out. But I was able to write the set C as a union, intersection, complement kind of thing using A and B. So for example, A union B, if you union these two sets up here, you get a set with three elements, heads, 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 tails, and tails, tails. And if you intersect them, you get one element, heads, heads. And if you complement the intersection and take that out of the original three-way set, you end up with just heads, tails, and tails, tails. So if you don't believe me, pause the video, take a moment to check that out. Because we were able to write this set C in terms of A and B using complements, intersections, and unions, then we know that C is in the sigma field generated by curly A1, because the sigma field has to be closed under complements and countable unions, and therefore finite unions, and therefore intersections using De Morgan's laws along with the complements. So the fact that we can represent C like this tells us that C is in fact in the sigma field generated by curly A1. But C is in curly A2 and therefore in the sigma field generated by curly A2, because we take that original collection of, in this case, one set, and we throw in other things we need to make it a sigma field. So the sigma field generated by a class of sets involves or contains everything in the original class. So C, being an A2, means it's in the sigma field generated by curly A2. And so we have just shown that C is in both sigma fields, and C is not independent of itself. So before I go saying that, we should think about that. Could C be independent of itself? For C to be independent of itself, we need the probability of C intersect C, which is simply the probability of C, to equal the probability of C times the probability of C. In other words, we need the probability of C squared to be the probability of C. And this can happen if C has the probability of 0 or 1. Now, that would happen if C is an empty set or the full omega, but it could happen for other sets that are not empty and the full omega. It is possible to have a set with probability measure 0 that is not the empty set, and to have a set with probability measure 1 that is not the full omega. For this particular set C, which consists of heads, tails, 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 the probability of C is 1/2, and 1/2 squared is 1/4, which is not 1/2. So in this case, C is not independent of itself, and yet C is in both of the two sigma fields. So I found something in each sigma field that is not independent of itself. So I have a set over here and a set over here, and they're not independent. And therefore, the two sigma fields are not independent, even though the original curly A1 and curly A2 were independent. So remember what we were trying to do. We were trying to say, if curly A1 is independent of curly A2, and you generate the sigma fields, they're still independent. And we just saw an example of that not being true. I did mention that you're going to have to add a very pretty subtle condition, I think. And so I have a definition for you. I'm going to take a collection of sets. We use those capital curly letters, and I'm going to use this capital curly kind of puffy P. It's going to be called a pi system. So that's why I used a P for pi. And a set of sets, curly P, is a pi system if it's closed under finite intersections. So that's a fairly weak condition. It's certainly weaker than a field or sigma field. Fields and sigma fields are both closed under finite intersections, and therefore both of them are pi systems. But pi systems do not necessarily contain omega, not necessarily closed on their complements, and so on. So the other direction, if you have a pi system, it's not necessarily a field or sigma field. I have another kind of collection of sets to talk about as well. I'm going to call this a capital script kind of curly L, and it's known as a lambda system if it has three properties. So just like with fields and sigma fields, we're going to have an I, double I, and triple I. For the definition of a lambda system, I is that it contains omega. So that's actually identical to I for the definition of a field or a sigma field. And double I for the definition of a lambda system is that it's closed under complements. And that's also identical to double I for the definition of a field or a sigma field. Now, I wouldn't be defining this if it was just a field or a sigma field. So here's where it's going to change. Triple I. Triple I for the definition of lambda system says that it's closed under countable disjoint unions. So a field had to be closed under finite unions, and they didn't have to be disjoint. A sigma field had to be closed under countable unions, and they didn't have to be disjoint. But here they have to be disjoint. So if you have a sigma field, it's already closed under countable unions, whether they're disjoint or not. In particular, it's already closed under countable disjoint unions. So any sigma field is in fact a lambda system, but a lambda system does not have to be a sigma field. So this is a little bit weaker than a sigma field. So continuing on in this definition, I claim that property double I, that it's closed under complements, can be changed out for a property double I prime, which looks like this. If you have sets A and B in the lambda system, with A being contained in B, then B minus A has to be in the lambda system. So B minus A, remember, is B intersected with everything outside of A. So it's like a complement of A, but within the set B. And this is a different condition that we can replace double I with. Now, I'm not saying that double I prime is equivalent to double I. I'm saying the rules as a whole, I, double I, triple I, is equivalent to the rules I, double I prime, and triple I. And let's see why. First of all, if you have I and double I prime, you have double I. Why is this? Because if you have I for the definition of a lambda system, then omega is in the lambda system. And you just need to plug in omega for B in double I prime. So if omega is in the lambda system and A is in the lambda system, then A is contained in omega, and omega minus A is everything inside omega and outside of A, which is just the regular old A complement. So this property here, if you take B to be omega, is the original double I, which just says if A is in lambda, A complement is in lambda. So this proves that if you define a lambda system with I, double I prime, and triple I, you get back to the one defined as I, double I, and triple I. Let's go the other way. Suppose I have double I and triple I holding. I claim this is going to imply that we have double I prime. To prove this, I want to take an A and a B in the lambda system with A contained in B. And our goal is going to be to show that B minus A is still in L. And I claim we're going to get that from double I, triple I of the original definition of a lambda system. So if B is in L by double I, we know that B complement is in L because a lambda system is closed under complements using that first definition. Under the assumption here that A is contained in B, if you look outside of B at the complement of B, that is going to be disjoint from A, which is inside of B. So I've got an A and a B in L because L is closed under complements by property double I, I've got that B complement is in L. And I know that A and B complement are disjoint. To finish this off, notice that B minus A is B intersect A complement. And we can use De Morgan's laws to write this as A union B complement all complement. So A was originally in L, B was in L, and that implied that B complement was in L. By triple I of the original definition of a lambda system, it's closed under disjoint unions. And A and B complement are disjoint, so A union B complement is in L. And by the original double I for a lambda system, if you have a set in L, its complement is in L, and therefore this whole thing is in L. So we have shown, starting with an A and B in L with A contained in B, that B minus A is in L, and that is property double I prime gotten from properties double I and triple I. So we're done showing that the two definitions for the lambda system are equivalent. Here's a fun fact for you. I claim that if a collection of sets curly A is a pi system and a lambda system, that it is a sigma field. To prove this, I want to look at properties I, double I, and triple I of the definition of a sigma field and see if we can get them from the fact that curly A is a pi system and a lambda system. So part I of the definition of a sigma field is that it contains omega, and we get that directly from part I of the definition of a lambda system. So we're done with part I of the definition of a sigma field. Part double I of the definition of a sigma field is that it's closed under complements. And we get that directly from double I of the definition of a lambda system. Now, the definition of a sigma field, part triple I, says that it's closed under countable unions. And it says nothing about disjointness. So how are we going to get this from a lambda system? And hopefully we're going to use the fact that it's a pi system here because I haven't used it so far in this proof. Let's take any countable collection of sets in curly A, call them A1, A2, A3 on up. And I want to use the fact that the curly A is in fact closed under disjoint unions. Now, these are not just joint, but we've done this trick before where we create disjoint sets. I'm going to let B1 be A1. I'm going to let B2 be everything that's in A2, but outside of A1. I'm going to let B3 be everything that's in A3, but outside of A1 and A2. We've sometimes seen this construction where we've had rings, but that only holds when the A's are nested. We can still have this construction if I have an A1 over here and an A2 over here and an A3 over there. I can let B1 be everything in A1 and then B2 be everything in A2 that's outside of A1. Maybe they don't intersect, maybe they do, but they don't have to be contained. So this is not necessarily one of those ring constructions, but we do have disjoint sets that have the same union as the original A's. Furthermore, the complements all used here are in curly A because it's a lambda system and it's closed under complements. And finally, because curly A is a pi system, it's closed under finite intersections. So I started with sets in curly A because it's a lambda system. These complements are in curly A because it's a pi system. All of these finite intersections, i.e. the new sets, B1, B2, B3, etc., are in curly A. These sets are disjoint, and the union of all of the B's is equal to the union of the A's is in the curly A because curly A is a lambda system and it's closed under disjoint unions. So our non-disjoint union is actually equivalent to a disjoint union, when looked at a different way. And so we do have that it is in fact in A, and therefore A is closed under countable unions, and that is part 3. And the final part to showing that curly A is, in fact, a sigma field. Now, we're still not to our main event here, which is the two classes and then generate the sigma fields and see if independence will translate. But we're working our way there. I've got a lemma for you. And this one I'm going to let you prove some of. It's very straightforward. And this is that the intersection of two lambda systems is, again, a lambda system. So if I have a lambda system, curly L1 and curly L2, I want to show that curly L1 intersected with curly L2 is again a lambda system. And I want to remind you that we are not intersecting sets from the lambda system. That's something different. So I'm not taking a set from one lambda system and another one and intersecting the sets. The intersection of the lambda systems are the sets that are in both. So common to both. So again, not taking one from each and then intersecting them. I'm only saying they're in the intersection if they are in both. And so if I start with lambda systems, I claim that this intersection of lambda systems is again a lambda system. So number one, or I, it needs to contain omega. Because each of the individual L1 and L2 were lambda systems, they both contain omega by property I of the lambda systems. So it's in both, so it's in the intersection. So omega is in curly L1 intersect curly L2. Same thing with a complement. If I take any set A in curly L1 intersected with curly L2, by definition, it is in curly L1, and by definition, it is in curly L2, because those are each individually lambda systems. A complement is in curly L1, and a complement is in curly L2, so it's in both of them, so it's in the intersection, and so we're done with property double I of a lambda system. Property triple I, we want to show that it's closed under countable disjoint unions. There's nothing particularly tricky about this one, so I'm going to leave it up to you, but you just have to take disjoint sets in the intersection of the two lambda systems and union them and show that that's still in the intersection. And it's going to work in a very similar way to our proof here for part double I. Now, before we get to the main event, I have one more lemma for you, and this one truly is a lemma in the sense that it's really just kind of needed to support something that's coming up next. You know, the last one, the intersection of two lambda systems is a lambda system. That's a pretty hefty standalone result, I would say. But this one is going to be unmotivated. The statement of this lemma is going to look very weird until you see how we're going to use it later. So please bear with me. I'm going to start with a lambda system, curly L, and I'm going to take any A subset of omega, and I'm going to define a new collection of sets, curly L sub A. And why am I calling it curly L? I'm being a little leading here maybe, but bear with me. This is going to be all subsets of omega, so I'm going to call those B, such that A intersect B is in curly L. And I use this curly L because I want to say this is a lambda system, and it's not in general, but it is if the original A came from the lambda system L that's being used over here. So again, I've got a lambda system. I take a set A from the lambda system. Then I look at a collection of sets such that when they're intersected with A, the result is in that original lambda system. And I claim that those sets that do that form their own lambda system. Let's prove it. We've got three things, right? So I'm going to take A in L and define this set. So that's just the setup of this theorem. And I want to show property I, double I, or maybe double I prime, and triple I for a lambda system for this L sub A. So omega needs to be in here, and it certainly is, because for omega to be in here, by definition of L sub A, I need omega intersected with A to be an L. But omega intersected with A is just A, and A is an L by the setup. So we're done showing that omega is in L sub A. I want to show it's closed under complements, and this one is surprisingly, I don't know, I think the trickiest one of the three here, and that's not usually the case. But let's show it's closed under complements. So I'm going to show property double I as opposed to double I prime. And I'm actually going to use double I prime on my way there. So A is already a fixed set defining this collection. So I'm going to take another set out of LA. Let's call it B. I want to show that B complement is also in LA. Now, because B is in LA, this means that A intersected with B is in L. That's how we define inclusion in LA. And A was given in L, and A intersect B is contained in A because it's an intersection of something with A, so that's going to be contained in A. And by double I prime, because L is a lambda system, what I have here are two sets, containment, and they're both in L. So this set minus this set has to be in L, because L is a lambda system and using property double I prime. But if we write out what this set is, well, by definition, this is A intersect this guy complement. By De Morgan's laws, this guy complement is A complement union B complement. I can distribute this intersection across, and then A intersect A complement is the empty set, so that part disappears. And we end up showing that A minus the set A intersect B is equivalent to A intersect B complement. So I know that this is an L by double I prime. And therefore, I know that this is an L. And that's what we wanted to show in order to show that B complement is in LA. For B complement to be in LA, when you intersect it with A, it needs to be an L. So we are done with part 2 of showing that LA is a lambda system. For part 3, or triple I, we want to show that LA is closed under countable disjoint unions. So take any sets B1, B2, B3, disjoint, and in LA, we want to show that the union of all of these is in LA, which means we want to show that the union of all of these intersected with A is in L. So let's consider the individual intersections, A intersect B1, A intersect B2, etc. These are all in L by definition of B1, B2, B3, etc. being in LA, because to be in LA, it means these sets, when intersected with A, have to be in L. These sets are also disjoint because the B's were disjoint. So I took a bunch of disjoint sets and I maybe intersected them with something that may intersect all of them or some of them, but those individual pieces you're going to carve out of the B's are still disjoint. So what I have are disjoint sets in L. And if you look at what we ultimately want to look at to show that the union of the B's is in LA, that is, if we look at A intersect the union of all the B's, you can rewrite this as the union of the individual A intersected with B's, and draw a picture, draw a Venn diagram if you need to convince yourself of this. But here we have a countable union of disjoint sets in L, and L is a lambda system, therefore this is an L. So if this is an L, that is how we define this set right here being in LA. And so we're done. We took a countable collection of disjoint sets, B1, B2, B3, etc. in LA, and we showed that the union of the B's is in LA. And we are done with property 3 of a lambda system. So we have shown that if you take a set A in a lambda system L, and you define a new collection L sub A to be all the B's such that intersected with A are in L, that is a lambda system. Now for the penultimate theorem for today. This one gets some stars. It's known as Dinkin's pi lambda theorem. And alone, maybe you're not going to care about this, but we're going to use this a lot for proving other things. So you might even think of it as a lemma. Sometimes they get named theorems, sometimes they get named lemmas, but this one mostly supports other things. So I think it's more like a lemma. And at first glance, it maybe will not seem like something you care about. But as I just said, we're going to use it over and over and over again. So eventually you're going to realize that you really care about this result. So I'm going to start with a pi system, curly P, and a lambda system, curly L. And if the pi system, which is a collection of sets, is a subset of the lambda system, which is another collection of sets, Dinkin claims that the sigma field generated by the pi system is still contained in the lambda system. Again, why would you care? I don't know if you care at this point. I know I do, but I know it's coming up. So this is going to help us prove many things, including the ultimate goal of this video, which is about the independent classes and expanding them to sigma fields and trying to say they're still independent. Let's prove Dinkin's pi lambda theorem. You might want to write this down or take a screenshot because the proof is going to take several slides and you might forget what we originally started with, but let's go. I'm going to start out by defining curly L naught to be the smallest lambda system containing the pi system P. I claim this means that L naught is sandwiched between curly P and curly L. And the reason for this is I can't remember if I called it a theorem or a lemma, but it's because the intersection of lambda systems is again a lambda system. So if L naught is a lambda system containing P, and supposedly the smallest such lambda system, if we had a picture kind of like this, where this is the collection of sets P and this is the collection curly L, and maybe curly L naught was containing P but not contained in L, then what we would have is a lambda system here and a lambda system here, and the intersection, which is in here, would be another lambda system. It would be smaller than L naught and containing P. So this would contradict the fact that L naught is defined as the smallest lambda system containing P. Therefore, we must have curly L naught sandwiched between curly P and curly L. If we can show that curly L naught is a sigma field, we're actually done, because the sigma field generated by curly P has to be contained in any sigma fields that contain curly P. So sigma of curly P would have to be contained in L naught if it was a sigma field, and this is contained in curly L from the statement above, and therefore we would have the final result that the sigma field generated by curly P is contained in curly L. So I am narrowing down what we need to show, and I kind of want you to forget about the rest because there's too much to remember here. Now we are down to the goal of showing that L naught is a sigma field. And once we do that, we're done with this proof. But L naught is a lambda system by definition. And we just had a lemma that said that if you have a lambda system and a pi system, then you have a sigma field. And we want to show that curly L naught is a sigma field and it's a lambda system. So if we can show it's a pi system, then we'll have that it's a lambda system. And then we are done with the entire proof of Dinkin's pi lambda theorem. This is now the remaining goal of this proof. So to be specific, we need to show that it's closed under finite intersections. So I'm going to take a set A and B in curly L naught, and we want to show that A intersect B is in curly L naught. This is the entire goal. The rest of the proof, we are finished if we can show this. So let go of the other stuff. There's too much stuff to keep in mind. Once we prove this, you are done. And if you don't believe me, pause the video, go back a few slides and go through those steps again and convince yourself that once we prove this, we are done. So let's go with this final part of the proof. I'm going to take any set C in curly P. Now A and B are fixed sets, right? So they're going to be fixed throughout the proof. So now I'm just taking an arbitrary set in P. I'm going to the next letter in the alphabet. So take a set C in curly P. Then C is in curly L naught, simply because P is contained in curly L naught. And this means that if you look at the collection L sub C, which is going to be all subsets D of omega for which C intersect D is in, I'm going to define this to be all subsets D for which C intersect D is in curly L naught, then curly LC is a lambda system because curly L naught is a lambda system. And so now I'm using the lemma just before this proof to conclude that curly L sub C is a lambda system. I've got a series of claims for you coming up. Number one, if C is in curly P, the pi system, then that means the pi system is contained in this new set we've defined, curly LC. To show that, I want to take any particular set in P and show that it's an LC. Now I've used up C to define this. So let me take another letter. I'm going to take set D in P. Then because C is in P and I just took a D in P, C intersect D is in P because P is a pi system and it's closed under finite intersections. And that means that C intersect D is in L naught because P is contained in L naught. But if C intersect D is in L naught, then by our definition of L sub C, D is in L sub C. So we're done with this claim. We proved it. We took a set D in curly P and we showed that it's in curly L sub C. So we have shown that P is contained in L sub C. For my second claim, I want to take a set C in P and a D in curly L naught and show that C intersect D is in curly L naught. Our ultimate goal here is to take an A and B in curly L naught and show that the intersection is in curly L naught. So this is like halfway there. I'm going to take something in P and something in curly L naught and show that the intersection there is in curly L naught, when really I want to take both sets from curly L naught, and we're on our way there. Now C taken from P and P contained in curly L naught implies that C is in curly L naught, and this implies that L sub C, as defined, is a lambda system. By claim one, we know that the collection, the pi system curly P, is contained in curly LC. But because curly L naught is the smallest lambda system containing P by definition, we have that it must be sandwiched between P and curly LC, which is another lambda system containing P. So curly P is contained in curly L naught is contained in curly LC. And this means if you take a D in curly L naught, because curly L naught is contained in curly LC, D is contained in curly LC. But if D is contained in curly LC, the definition of curly LC are all the sets that if you intersect them with C, you are in L naught. So this means that D intersected with C is in curly L naught. And that's what we're trying to show, that C intersect D is in curly L naught. So we're done with claim 2. The third claim I want to show, and there's only one more, we're almost finished, is that if C is in L naught, then P is contained in curly LC. So these are probably all blending together for you right now. This is pretty similar to claim 1 inside this proof. And again, I think it's going to help you to take notes or screenshots so you can lay them out next to each other. This is kind of hard to do in a video as opposed to a classroom where we've got a whole bunch of boards where this all can be in front of you. But yes, this is similar to claim 1. So I want to show that the pi system is contained in curly LC. So I want to take any set D in the pi system and want to show that it's in curly LC. Now, by claim 2, C intersected with D is in L naught. That's what we showed. This is exactly claim 2. We took something in the pi system and something in curly L naught and showed that the intersection is in curly L naught. So exactly claim 2. But if C intersect D is in curly L naught, that means that D is in LC, and we're done. So that one was pretty easy because that's how you define inclusion in curly LC. The final claim, this is the money claim. This is what we're actually trying to prove. Take a set A and B in L naught. We want to show that L naught is closed under finite intersections and therefore is a pi system and therefore is a sigma field. And therefore we have proven Dinkin's pi lambda theorem. So if A is in curly L naught, that means that the collection of sets curly L sub A, which is defined as all sets when intersected with A, give you a result in L naught, is a lambda system. That was the lemma right before this theorem. And so by claim 3, I've got that P is contained in curly LA. But curly L naught was the smallest lambda system containing P. So curly L naught must be contained in curly LA. So far, I've only used the fact that A is in curly L naught, but now let's use the fact that B is in curly L naught. Because B is in curly L naught, it is in curly LA. And that means that B intersected with A is in curly L naught. And that's what we wanted to show. So we're done with showing that curly L naught is a pi system. And so we are done with proving Dinkin's pi lambda theorem. And now here we are at the ultimate goal for today's video. I have a collection of sets curly A1 independent of a collection of sets curly A2. I want to expand each into a sigma field, and I want to show that those are still independent, and we know that that's not exactly true from our example with the coin flips at the beginning of this video. But I claim it is true if we start with 2 independent pi systems. And a pi system, that's not that strong of an assumption to put on something. I don't know, I guess it's all relative to other assumptions you might put on there, but I'm not claiming that they need to be, well, anything other than a pi system. So in general, if I have classes of sets curly A1, curly A2 out through curly AN, independent pi systems, I claim that the sigma field generated by curly A1 is independent of the sigma field generated by curly A2, is independent of that they're all mutually independent collections of sets once you expand them into sigma fields. To get away with the kind of easier way of looking at independence, where you look at n-way intersections and n-1-way intersections and n-2-way intersections, I want to throw in omegas, right? Because as we said before, A1 intersect A2 intersect A3 is simply A1 intersect A3 if you allow A2 to be omega. So I'm going to change the collections of sets. I'm going to call them curly BIs. And curly BI is going to be curly AI with the set omega thrown in if it wasn't there already. Note that curly BI is still a pi system because it needs to be closed under finite intersections, and throwing omega in there is not going to change anything. Omega intersected with itself is still omega and it's in there. Omega intersected with anything in there is the original set, which is certainly in there. So still a pi system. Furthermore, the sigma field generated by curly BI is the same as the sigma field generated by curly AI. Think about it. If you have a collection of sets, curly AI, and you want to expand it to a sigma field, you use those original sets and you have to throw in complements and countable unions, and you have to throw in omega if it wasn't there. So curly BI is something you get starting with curly AI and starting to fill it out to a sigma field. And so you're going to end up with the same result if you already had omega in there or didn't already have omega in there, because probably the first thing you're going to do is throw omega in there. So the sigma fields generated by the curly BIs are equivalent to the sigma fields generated by the curly AIs. And so ultimately, I want to show that these sigma fields are independent. Recall our definition of independence of the original curly A's. We need to take any sets A1, A2 out through AN, where AI comes from curly AI, and we need to show that the intersection probability is the product of the original probabilities. And we need to look at n minus one of them and n minus two of them, but we got around that by just saying, why don't you allow the sets to take on the value omega, because that'll give you those smaller intersections. In other words, this is our easier way to show independence of the curly A's, and it's built into our curly B's. So basically, we now have that the curly B's are independent if and only if the probability of B1 intersect B2 out through Bn is the product of the individual probabilities. And of course, that independence here follows from the independence of the curly A's. This proof is going to be kind of a constructive thing where we're first going to look at the sigma field generated by curly B1 and show it's independent of the other B's, and then the sigma field generated by B2. So fair warning, this is going to be maybe a little disappointing at the end, because I'm going to prove that first part and then sort of say ... on the end. So consider for any I being 2, 3, 4 up to n, I'm going to fix sets. So I'm going to fix a set B2 from curly B2, B3 from curly B3, etc. And I'm going to define a collection L to be all sets in the underlying sigma field. Yes, there is an underlying sigma field to everything we're doing. I could have started this whole video with let omega be a non-empty set, let F be a sigma field, and let P be a probability measure so that we have a measure space. So I'm going to let L be all subsets A of the sigma field for which the probability of A intersect B2 intersect B3 out through intersect Bn is the product of the individual probabilities. So certainly, if I take a set B1 out of curly B1, it is in L. In other words, curly B1 is a subset of L. And I claim that curly L is a lambda system. So to show it, we have three things to show: I, double I, triple I, or I, double I prime, and triple I. So we need to show that omega is in L. So if I plug in omega for that A in the definition of L, we've got the probability of omega intersect B2 intersect B3 up to intersect Bn. And this is just the intersection of the n minus 1 sets, B2 up through Bn. Because the BIs come from the curly BIs and those collections are independent, I do know that this factors. And because the probability measure of the full omega is always 1, I can rewrite this as the probability measure of omega times this product. So if you look at this left side to this right side, this being true tells us that omega is in L, because this is what it means to be in L. A set plugged in here has to give you a probability that factors like this. Let's show that it's closed under complements. I am going to take a set A in L, and that means that the probability of A intersect B2, intersect B3, etc., factors into these individual probabilities. Now, I want to show that this would hold if I replace the A in this statement with A complements. So to that end, I'm going to take this n minus 1 way intersection over here and call this B, just so I can refer to it in an easier way. Note that the probability measure of B can be written as the part that's intersected with A plus the part that's intersected with A complement, because those are disjoint sets whose union is B. So we're using finite additivity of a probability measure because those are disjoint. This thing on the left side is the product of the probabilities of B2, B3 out through Bn. On the right side, this first term we just saw is the product of the probability of A times the probability of B2 out through the probability of Bn. And then this last term is whatever it is. I don't know what it is. This is what we're going for right now, but I can expand the B out into the intersection of B2 through Bn. And then if we move some things around here, for example, if I isolate this term and move this to the other side and factor out all of this stuff, then I've got that this term is equal to 1 minus the probability of A times a product of a bunch of B probabilities. But 1 minus the probability of A is the probability of A complement. And so we have shown that the probability of A complement intersected with B2 intersected with B3 on up is the product of the probability of A complement and the probability of B2 and the probability of B3 on up. And this is what it means for A complement to be included in L. This is the rule. So we're done showing part 2 of L as a lambda system. We've shown that it's closed under complements. Part 3, or triple I, for showing L as a lambda system, I want to take disjoint sets in L. I want to show that it's closed under countable disjoint unions. So let's consider the probability of this countable union of the A's intersected with B2, intersected with B3, out through Bn. I can rewrite this as a big union of each individual A intersected with all of the B's. Because the A's are disjoint, if I intersect them with other things, disjoint or not, I'm not going to suddenly get the A's to have common parts. So these intersections are still disjoint sets. And I can use countable additivity of the probability measure to rewrite this probability of a union of disjoint things as a sum of the individual probabilities. But the AMs are in L. And by definition, this probability can be written as a product of probabilities like these. Now, these probabilities involving the B's, there's no M over here. So these are a constant in the sum. I can pull all of these out in front of the sum. I'm not going to actually write that line. This is just taking up more space. But when I do that sort of maneuver, I'm left with the sum of the probabilities of the AMs. I'm summing over M, and I can use the fact that they are disjoint and use countable additivity going the other way to write this sum of individual probabilities of disjoint events as a probability of a union. And if you look at this from here to here, this is how you show that the union of the A's is included in this curly L, which has been defined to be sets that satisfy this kind of property. So we have finished showing that the countable union of disjoint sets from L is still in L. So we have finished showing that L is a lambda system. We already mentioned that B1 is contained in L because if you take any set B1 from curly B1, then because curly B1 is independent of curly B2 and curly B3, then we have this thing factoring if you replace the A with any B1 from curly B1. So curly B1 is contained in L. And from the very beginning of this proof, when we defined curly B1, we noted it was a pi system. And we just saw that L is a lambda system. And here's where Dinkin's pi lambda theorem comes in. I've got a pi system contained in a lambda system. So the sigma field generated by the pi system is still contained in the lambda system. This is Dinkin's pi lambda result. But recall that the sigma field generated by curly B1 is the same as the sigma field generated by curly A1. But look at how we define L. If the sigma field generated by curly A1 is contained in L, then any sets A1 from the sigma field generated by curly A1 have to plug into this expression here. And this expression has to factor in this way. So what we have shown when we conclude that the sigma field generated by curly A1 is contained in L, we've shown that for any A1 in the sigma field generated by curly A1, we have this factorization for any sets B2, B3 out through Bn from the respective curly B's. And this is how we show that the sigma field generated by curly A1 is independent of the class curly B2 and curly B3 out through curly Bn. And equivalently, the sigma field generated by curly A1 is independent of the class curly A2 and the class curly A3 out through curly An. So we started with a bunch of curly A's that were independent, and we turned one of them into a sigma field and still have an independence. And we did that by defining this thing curly L as a very special lambda system. So we are on our way to putting sigmas on all of these. Let me just give you an idea of how you would get the sigma on the next one. I would fix a set A1 in the sigma field generated by curly A1. I would fix sets B3, B4 up through Bn from curly B3, curly B4 up through curly Bn. And I want to get the sigma on the curly A2 now. So I'm going to define a new lambda system L. I'm using the same symbol to be all A in the sigma field for which the probability measure of A1 intersect A, intersect B3, intersect B4 out through Bn is the product of the individual probabilities. This is very similar to what we did for our previous definition of L, except that now we're starting with something in the sigma field we've already formed. Now you just want to go through the same steps. You want to show that this new collection L is a lambda system. You want to note that curly B2 is a pi system and contained in L. You want to use Dinkin's pi lambda theorem to say that the sigma field generated by curly B2 is contained in L, and that's equivalent to the sigma field generated by curly A2. And so this means that for any set A2 in the sigma field generated by curly A2, we've got P of A1 intersect A2 intersect B3 intersect out through Bn is the product of the individual sets. Since this has to hold for any A1 in the sigma field generated by curly A1, and for any A2 in the sigma field generated by curly A2, and for any B3 in curly B3, and for any B4 in curly B4, etc., we now have that the sigma field generated by curly A1 is independent of the sigma field generated by curly A2, is independent of the collection curly B3 and curly B4 out through curly Bn. So we've now got two sigma fields in there, and you just have to keep building it up until all of these are the sigma fields that we'd like to see. In other words, until we have that the sigma field generated by curly A1 is independent of the sigma field. I should stop saying it that way. It is a mutual independence. So the sigma field generated by curly A1 and the sigma field generated by curly A2 and the sigma field generated by curly A3 out to the sigma field generated by curly AN, those are all mutually independent. And those are the steps you need to prove this theorem. I claim that this theorem also can extend to an infinite collection of collections. So not just a curly A1 through curly AN, but maybe a countably infinite number or even uncountably. And the only reason that, or not the only reason, but the reason that that's so easily proven is that's the definition of independence when you've got an infinite number of classes you're looking at. You need to take any finite number and show they're independent, no matter what finite number and no matter which of the classes you chose. And each of those can be shown to be independent using the previous theorem. So that was a little hairy, but it's more notational than anything else. And Dinkin's pi lambda theorem, that proof was a little bit tricky, but we did it. Now in the next video, we're finally, I promise you, going to get to the famed Borel-Cantelli lemmas. We're going to establish sufficient conditions for us to say, if we have a sequence of events, A1, A2, A3 on up, that the probability of the limb sup of the events is in some cases 0 and in some cases 1. And remember that the limb sup of a sequence of events can be interpreted as infinitely many of the events are happening or not happening. So we're going to be able to draw some conclusions about that happening with probability 0 or 1. In other words, we're going to be able to conclude that events are going to happen an infinite number of times or only a finite number of times. And it's really cool. These are some of my favorite theorems in measured theoretic probability, the Borel-Cantelli lemmas. So I hope you come back after that pretty hairy day today. I hope to see you in the next one.